Hello, thank you. Welcome to this recording. Today we're going to talk about QSPI Flash on the FPGA. This is kind of critical for FPGAs because you load your bit file from the flash, and being able to update the flash during the field to be able to update your bit file, to change stuff, and maybe change out. So sometimes you will store your software in your flash as well. You'll have the bit file, and you'll have a first stage bootloader type software, and maybe load up software from somewhere else or something like that. But this is important to be able to change your FPGA firmware in the field. So let us talk about how our QSPI is positioned. So this wonderful diagram, we have our PCIe going through this PCIe bus to this switch. The switch is connected to this quad SPI. Anything important here? Quad SPI, Vanishing device, pipe of death. That's important. Startup primitive. So the reason we have to have the startup primitive here is because this flash is connected to the startup pins, and so it automatically has to go to those base configuration pins. And if we just had QSPI on some generic IP, we would turn that off. But that's about everything we need in here. Search for the performance, and now you can tell me. So address editor. If we look, the QSPI is at that address. That's important. That's kind of what the code's based on, but we'll get to that. So let's dig down into the hardware of this guy real quick. Going to this guy, right? So it took me a while to get this up and running, so I can understand it's complicated. Or there's some nuances that aren't explained clearly. Not necessarily it's complicated, but it's explained well. So we have these registers. We have our reset register, our control register, our status register, our transmit FIFO, or receive FIFO, a chip select. So this is actually a chip select. I didn't realize that so much until later when we're not going well. The occupancy, the FIFOs. I don't really use the interrupts because I'm not using a processor. I'm just using Python code. Some Python code to read and write this stuff. So yeah. Okay. We go through the registers. Our reset register takes a specific value to reset. Anything we want, we're in QSPI mode, so I mean a lot of these settings where we wanted that was already set. We wanted this to be in master mode, not slave mode. Master configuration, stuff like that. Nothing terribly complicated. Status register. There's useful information here. I didn't use it as much as I should have in my code. Maybe I'll go back and do it. Then we have our spies. So the slave select. Important thing to note is that it is active low 1 hot encoding. So what happened when I was doing this earlier is I wasn't enabling the process or enabling the flash component, which is the chip select and the flash component, and my reads were all Fs. And then when I did set it, once I activated it, I didn't deactivate it. And what happened is like my if I was doing a read, the read would continue to do the entire page or something like that. So it's important to maybe toggle your chip select between commands, which proved to give me more consistency. I mean, that's all in the QSPI documentation, but this is kind of what you see from the software side. And yeah, so that was basically it. There was nothing terribly complicated with this, except just some nuances I had to go hunt down. Okay. So that's kind of like, this is the steps I take to understand these devices. So we go next. Our next thing I usually hit up is if we go to SDK, they usually have, so blurry right now. I make the screen bigger for you guys. So if you go to your the board support package or something like that, they usually have a SPI driver software. And you can go to this driver software, and it has has examples of how it does, or like it has the functions where it does the transactions for you and whatnot. And I kind of went through the place and put in little print statements to kind of peek and poke at the code to see what it was doing, to make sure I understood what it was doing. Much nicer than my code, but my code's running on Python on a Linux machine over PCIe, running off the microblaze. And we can run it off the microblaze, like right here, running off one of my processor or one of my devices. And it read the kind of the first page of the flash. One thing to note is I like the first five thing are kind of connected to a command, so it's not necessarily correct data. Yeah, I think that is where it lands. Okay, is it 25 here as well? Yeah, but yeah, 5. Okay, so yeah, it's just reading it from the microblaze using their software. World. Yeah, and so in their software, you can initialize it, set some options for master mode, um, do the select, what chip select you want to use, and then this is to do a random read at address 0, transfer, and just for loop through the receive buffer. So basically, some simple microblaze code for accessing that. Getting what's actually saying. Oh, nothing yet so far. So that's kind of the simple microblaze code. Now, where are we going? I really need to get some sleep. But we'll finish this little conversation. So once we have that, let's look at how we're going to access it via software. So here, the Night Fury is the open source GitHub for the FPGAs I'm using, and he has a good software examples of using to like to write the flash, to erase the flash, to read the flash, to read the status register and stuff like that. Shows examples of how he adds the address in what order, what Indianness, which I've kind of copied. We'll go through my code in a second. And then here is the actual flash documentation, and it talks about this address space, being able to see things, status register, and then it's like, oh, if you want to read a status register, you want to use this command. Write enables status register. Talks about the bits, reconfiguration, write registers. I think it's important when doing these registers. And down here we have our read. So I'm using the 13H, which is just a generic read. I don't really have it set up for these other reads. I wonder if we can do the quad IO read. Not necessarily sure how that works. But we have the SPI hooked up. Running. Okay. How are we doing? Good. About 10 minutes. So yeah, there's a lot of documentation you can read, a lot of examples you can look at. So it is overwhelming. There's a lot of different things. You got custom hardware interacting with a chip, a device off chip, using special configuration ports, and you're dealing with a flash memory. And I mean, especially you don't want to screw it up, because if this is your only way to kind of like without plugging in JTAG, the only way to like reconfigure the device, you don't want to screw this up. So it can be important, but there's definitely plenty of documentation, plenty of things you can look at to understand what's going on. So We're going to run through my code example real quick, and then we'll probably end this video rather shortly. So here is my nasty code. So this section right here is reading the ICAP. It's reading, so like up to here. This is all just reading the ID code. I can go. If we go back here, scroll up a little bit. So all it's doing is reading the ID code for the ICAP, and I'm doing this for different tests. And this is the kind of all the ICAP addresses for reading and writing. But we'll ignore that for now. So we're going to start here. SPI verify. So the first thing we do, address 40, we send in the reset. So this is going to be the smallest byte, and these are the upper bytes. So we want the 0000A is going to look like that. And then this is a simple configuration to put in master mode. And then this is the chip select. So we talked about it was active low, one hot. So this is our active low. We've enabled the chip select on that device. This is us reading some status register. These are interrupt registers, just to read what those are. That is our status, or no, it's a control register. That's our status register. These 70 is our chip select, and 74 and 78 are our occupancies. So we're going to do a random read. We're going to do 128 bytes, and we're going to write this all to our out FIFO. And then we're going to read the status as we do it. I don't need to read status every time. Put a quick little why it's doing that, so we can talk about it. We know it's working. About so once we get our read going, so we create our FIFO, we put in plenty of bytes to be able to do a generic read. We're going to do some more status reading, chip select, and see right here, we flip that low. That's we're enabling the control bit for this device, reading a bunch of status because I'm curious what's happening, and I was debugging the snot out of it. And then we wait a second because I just want to make the read go through. It can go a lot faster than this. We stall the device again, and then right here is the receive FIFO. We can read from the receive FIFO. So that's kind of the first stage. So I can run that for you real quick. So what's going on? The password, because all Python memory accesses require. So yeah, and this is the beginning of every single bit file. This is the kind of like, use this to gauge the width of your interface, whether it's 8, 16, or 32 bits. The more don't cares. They call this the sync word, and then this is where the data starts coming into play. These are kind of raw configuration commands, and they usually associate with like the ID code. So let's see if the ID code's here. So the ID code is 1363, 1663. See if we can see it like a 93 here. The ID code has to be here somewhere. Might be later. That's okay. Let me see, was the ID code here at all? 3. $60. Yeah, so that's kind of good right there. And that's just reading our page. So let's talk about what the code is doing next. So what the code is doing next is this is the file I used in Vivado to program the flash memory. And if we go check that out, it's kind of has some fun configuration. So the first two, the first byte explains how many bytes of data it has. The next four are the address. The next two are the type. Then you have the data. Right here, this is two bytes of data, and then you finish up with the checksum. And I have a really fun regex expression where it goes number of data, the address, the type, and the data. And if you hit group 5, that would be the checksum. I don't really do the checksum. And then I stick this into a huge byte array. So this is the data I guess I'm expecting in the flash. So that's the data I expect in flash. Next, I am going to read the flash. So we do the random address read, but instead of doing zeros, the next 4 bytes, like was shown here, next 4 bytes, we're going to do the address. And I simply take my my I value and I convert it to a byte array, big endianness, and then I just write that byte by byte to the input buffer. Then I just fill the input buffer with the size of how many I want to read, and then we just do the transaction. Easy peasy. And then we read the values. The first 5 bytes seem to be kind of buffer from your command and address. That was fun to diagnose. And then here, using the zip command, I compare the bytes of the file to what I read from the flash. And if they don't work, we say sad, and then we kind of print out the range around them to see if we could debug it a little bit, and then we break and exit out. So before it was breaking or whatever, now that I do it, it'll take a while. It has like 5 million different writes it has to do. So that's kind of what I've been working on today to try to get the flash to work. So I'm confident I can read the flash. So the next step is, can I be confident that I can write to the flash? To write to the flash is a little bit different. So the flash has 2 actions to write to it. It has a write command and it has an erase command. There we go. And since there was no bad, what we read in flash is exactly what we got in our file, or at least what we scripted from the file. So there's 2 actions to flash. There is a erase command. An erase command takes an entire sector and converts it all to zeros. And then there's a write command. A write command can take any 0 and turn it to a 1. And that's basically how flash works. You can do random 0 to 1 changes anytime you want, but you have to erase an entire sector, which takes more power, more time. You want to take a 1 to a 0. So it's interesting because you can actually do multiple writes to a flash and just slowly change the zeros to 1. But yeah, it's a large section. So I think if we look down here, they said in his notes, entire sector was 64 times 1024, 256K. That's huge. That's what happens when you erase stuff. I'm trying to think if he has sector bytes here, this should be 64K, right? I don't know why. I may have to investigate that, or maybe let's see if we go to the erase right here. Go find the erase command. Erase. Where is the? If I type in erase. It says it erases 256K blocks for software compatibility. Oh, we have a 4K byte sector erase and a uniform. go figure out where these erases. Erase. Okay, so we have two sector sizes for erasing. We have 64K and 256K for our FLS device. See if we can find. So okay, so yeah, let's go see if we can figure out the. Where is Mr. Erase command? Erase there. It's probably useful if debugging. And close. And close. Okay. We have a sector erase and bulk erase. Curious to what these do. Block protection. Ready to explain the learn about the erase. Those commands. What does he have for his sector erase? He has a DC. That lines up with this command right here. Where do you specify 4K versus teach me your ways? Okay, so fine. Where's the DC? Or by the red erase. Um, yeah, I don't know what's up. It doesn't really. I might have to specify it, but yeah, here you go. It has an example of doing the command, providing the address, and the chip select should go back up. And that's how you do it. Here's the bulk erase. Oh, erase sets zeros to ones, and then write sets one to zeros. Okay, Andy was wrong. It's flipped. It's flipped on the write and reads. The erase sends it to ones. The write sends it to zeros. Okay, so yeah, my next step is to learn how to do an erase and do writes, and then be able to rewrite the flash. We'll see if I have time to do that tomorrow. I should really get to bed. Thank you for watching. I need to start posting some of these to YouTube. My YouTube channel seems to be picking up some momentum, which is surprising, but people find this stuff useful. So, yeah, if you have any questions, feel free to find the YouTube video. My Twitter handle is someplace. direct message me. Feel free to talk to me. I'm fine talking about this stuff. Have a good night. Bye.